We got a meter stick. It's set on the edge of a table so that all but a negligible, meaning ignorable, bit of its length is off the edge of the table as shown. The meter stick is released from rest horizontally. The meter stick's mass is m, its length is L, and the rotational inertia of the meter stick about its end is 1/3 ml squared. So they will always give us the rotational inertia or make it easy to find from another equation. So sketch a force diagram for the meter stick just as it's been released, meaning that it is still horizontal in this position, infinitely small moment of time later. But there's no longer anyone holding it at the end of the meter stick. Remember that a force diagram differs from a free body diagram and that the forces are drawn at the point of application rather than just the center of mass. So one thing is we've got gravity pulling on it. The center of mass is right in the middle, and so we've got this force of gravity. I'll label it right there, pulling down on it. We've also got the table is pushing up on this tiny little end, so there is a normal force, I'll call it, right there at the edge. This one has to be smaller than that one because overall the meter stick is moving down. So linearly, we know we have a net force down because we were at rest and now we're moving downwards. We accelerated downwards, it's better to say, and so the down force must be greater than the up force. They tell us to put an X at the point of rotation. So the point of rotation is right there at the edge of the table. You can actually pick wherever you want to be the point of rotation, but it's best to use this for several reasons in this problem. One is they already gave us the rotational inertia about the end. Because remember, objects can have different rotational inertias depending upon what you're spinning them about. So this would have a different rotational inertia if we spun it about the middle, or if we spun it like this way. So that's the main reason why we don't want to change this from being the point of rotation. The other advantage actually is though, we don't have to worry about any torques caused by the normal force because there's no lever arm right here. It's right on the point of rotation, and so that guy will not be a factor in the problem. So that actually answers the question, is there more than one pivot point? Yeah, for sure. But as we just mentioned, there's advantages to keeping it there. So now they say determine the net torque here about the meter stick's left end. So let's think about what torque is. Torque is the force acting on it times the lever arm times the sine of the angle between those two forces there. So we know what the force is. The only one left is the force of gravity. So if you want it, you could call this the torque caused by gravity. So this would be the force of gravity. The lever arm. So where is that force of gravity acting? Remember, it is acting right at the middle there, the center of mass. So this lever arm right here should be the length of the meter stick over 2, and it's acting straight down, so the angle is 90 degrees. So if we clean this up a little bit, we get the torque is equal to, the force of gravity will be mg, we'll have L from the length there. This will just become 1, the sine of 90, so that drops out, and then over 2. So that is the torque, mgl over 2. Notice the longer the meter stick gets, even if somehow we could keep it the same mass, the more torque we're going to get because we move that center of mass outward. So the next part, it says, starting with Newton's second law in rotational form, derive an expression for the initial angular acceleration of the meter stick in terms of m, L, and physical constants. So they want you to write the equations here and the description here because I need room to write it big enough for you to see. I'm going to actually write my equations here and just say the descriptions. So I'm going to start with Newton's second law in rotational form. The angular acceleration is the sum of the torques over the rotational inertia. It's just like A equals F over M, but it is the rotational form there. So second part is we just solved for the net torque. All we have is the torque of gravity, so I'm going to plug that in. We know what the net torque is. So we decided that the torque was mgl over 2, and then we're going to divide all of that net torque by the moment of inertia, or the rotational inertia, it's also called. Third step, I know what the rotational inertia is. They told me. They said it's 1/3 the mass of the meter stick times its length squared. So I'm actually, because I see what's coming here, I'm dividing by it. I'm going to write it as a fraction so I can multiply by its reciprocal. So I'm going to write it as ml squared over 3. And I think this will become a bit obvious why in a moment here. So now let's plug it in. We've got our angular acceleration. We've got our net torque already written, mgl over 2. We're dividing by our rotational inertia, so that's the same thing then as multiplying by its reciprocal. So I'm going to write it as 3 over ml squared. Some things cancel. Even though we wrote it as a little m there and a big M there, it's the same m. And there's an L up here which will cancel with one of those L's down there. So let's now just clean it up a little bit and write that the angular acceleration here, I'm going to pull my constants out front, are 3/2 g over L. Notice how fast is it going to pick up angular speed, radians per second per second. Part of it's a function of the planet we're on, and another part is the length. The bigger and bigger the length of this meter stick gets, well, I guess it wouldn't be a meter stick then, but what if we had a 2-meter stick? It would take longer to pick up speed in that case. So last part here is, it says derive an expression for the linear acceleration here of the far end of the meter stick. So in terms of g. And so let's go ahead and do that. I don't know if you remember from class, but I gave you an equation that allowed you to find the old school, the linear acceleration based upon the rotational acceleration. And you simply multiply by the radius. So you take your rotational or your angular acceleration and multiply by the radius. So let's start to plug in for those. We just solved for the angular acceleration. It's 3/2 g over L. And then we multiply by our radius. Well, out at the end, our radius is L. So our L's actually cancel out, and we get 3/2 g. In other words, think about what this is saying. At the end there, we're actually, as we fall here, we are going at 1.5 times g. How's that possible? Well, the meter stick as a whole is falling at g, but that kind of causes the end there to be whipped around with the rest of it. And so you actually will have a greater acceleration. So their question here is, what would happen to a penny placed on the end? The penny would actually lift up off of the meter stick, because the penny's going to accelerate at g. And the meter stick itself, because it's getting pulled and whipped around by the rest of the meter stick, that far end accelerates at 3/2 g.